Hello everyone, this is the 7th edition to the matrix decomposition series, and today we will be using householder matrices to carry out the QR factorization. If you're not sure how householder matrices work, check out my last video to learn more about them. So the basic idea of this factorization is that given a matrix A, we're going to go ahead and multiply this matrix by a string of householder matrices to essentially row reduce our matrix and put it into row echelon form. The byproduct of using householder matrices is that we can easily invert them since they're orthogonal and then find an appropriate QR factorization where Q is orthogonal and R is row reduced. Recall the definition of a householder matrix. To form a householder matrix that will aid us in our row reduction, we must derive a formula for choosing this unit vector U. Our goal is to find a householder matrix that can turn a column in our matrix into a column that has one value in its first entry and zeros all the way down. So geometrically, say our first column vector looks like this. We want to find a unit vector such that when we reflect our column vector across the perpendicular axis of our unit vector, our resulting vector ends up on the x-axis. Now, a key property of orthogonal matrices that we have not discussed yet, but is really important and it's really easy to prove, is that orthogonal matrices preserve magnitude. Hence, our resulting vector will have the same magnitude as our original vector. We can represent this new vector as a magnitude of A times the vector E sub 1, which is essentially the vector 1 followed by zeros on the rest of the entries. Now, let's derive a formula for U. For now, we're going to go ahead and ignore what H does to the rest of the matrix and simply zone in on the first column vector. We want H times A to be equal to the magnitude of A times E sub 1. Let's write this in the definition of the H matrix, and we can then go ahead and expand the left side. Now let's move some things around and we end up with this equation. Notice that U transpose times A is simply U dotted with A, which is just a scalar. So we can simplify that. From here, we use a little bit of geometric intuition. Recall that this equation is essentially saying that a vector is equal to another vector. Hence, in order for two vectors to be equal to each other, their directions must match. In other words, if we find the unit vectors of each vectors on both sides, they must be equal as well. So for the left side, we take the magnitude of the whole vector and divide it by the vector itself. And on the right side, since we have a scalar times a unit vector, we can simply drop the scalar. And there we have it. We have found a formula for U. Now, before we can jump into an example, the last thing I want to discuss is how we eliminate columns after the first one. The easiest way to do this is to treat the lower half of a matrix like a new matrix that has its own householder matrices that we can use to row reduce it using the same formula that we just derived. To put this into perspective of the bigger matrix, what we're actually doing is we're multiplying our original matrix by the householder matrix we found for our smaller matrix, and then we have these extra rows and columns that simply ensure that the other entries in our matrix that are already reduced don't get changed. We can simply carry out this process for the rest of the matrix to get our QR factorization. Okay, now let's jump into an example. Since these usually take a while for big matrices, I will be sticking to a 2x2 matrix, but using the technique we've discussed, you can extrapolate this factorization to bigger matrices, and again, matrices that are rectangular. Cool, so let's say we want to find the QR factorization of this matrix using the householder QR factorization. So let's use this column vector to form a unit vector and find our householder matrix with this formula. Now, using this unit vector, we can plug it into the definition of a householder matrix like so, and this is the householder matrix that we get. Now, if we multiply this householder matrix by our original matrix, we can see that the second element of the first column becomes 0. Now finally, to find the QR factorization, we will have to invert H so we can isolate our original matrix A. Since H is orthogonal, its inverse is simply its transpose. And as we discussed in the last video, the householder matrix is also a symmetric matrix. So this simply means that its inverse is itself. So now, when we multiply both sides by H, we get the following equation. Since in our case we only have one householder matrix, our Q matrix will just be our H matrix. Cool. Now if you had a bigger A matrix, you will have more householder matrices to multiply and invert, but the process is very similar and it's really not that much harder. Alright, that is all. That is how we find the QR factorization of a matrix using householder matrices. For anyone looking for a more detailed example, I've put a link in the description to a worked out example for a 3x3 matrix. Alright, that is all for today. In the next video, we'll be looking at the famous eigenvalue decomposition. So stay tuned for that one. Thank you.